All right, good morning, everybody. We're going to talk about population dynamics today. We're going to talk about how populations grow. There are some math problems that are on your equation sheet, so we're going to try some math problems after we go through these notes. So these and then the Simpson's diversity index are the math problems that we'll be doing in this unit. Okay, so let's just talk really quickly about population growth. And this is like so obvious. Organisms enter a population in two ways. So that's how the population grows, either by births or by immigration. And the population decreases, or organisms leave the population either by death or immigration, leaving the population and going somewhere else. There's two types of growth that we talk about. We talk about exponential growth and we talk about logistic growth. And we're going to look at kind of some math on both of them because they both exist in nature. It's just that one is not as common. So it says in exponential growth, my picture's in the way, everybody. In exponential growth, a population's per capita. Now, that's a word that maybe isn't familiar. So you need to think of per capita as per individual, each individual in the population. Let me say it again. In exponential growth, a population's per capita or per individual growth rate stays the same regardless of population size. So, however many they normally produce, that's how many they keep producing. As the population gets bigger and bigger and bigger and bigger, we see exponential growth. That's, for example, a really easy example would be if I had a beaker full of nutrient broth for bacteria and I introduced one bacteria. The bacteria would divide into two. It has tons of food. It has an entire beaker full. They would divide into two. They would divide into two. They would divide into two. And we would see exponential growth until my nutrient broth started to run out. And then we'll get to that. So it says the growth rate stays the same. They're going to double in my example, regardless of population size, making the population actually grow faster and faster as it gets larger. Exponential growth is represented by the blue line in the graph here. So you can see that speeding up, even though the population growth is the same, it's making the population grow faster and faster. So it says in nature, populations may grow exponentially for some period, like my bacteria, but ultimately they will be limited by resource availability. In logistic growth, that's the red line here, a population's per capita, per individual growth rate gets smaller and smaller as population size approaches a maximum imposed by limited resources in the environment. And this is a term you absolutely need to know. The term is carrying capacity, and you need to know it's represented by the letter K, which is annoying because it doesn't start with a K. Anyway, it's called carrying capacity, and that's going to be important as we do our math on this. So carrying capacity, for example, in my nutrient broth example, although that's a little bit complicated, but it's the maximum number of bacteria that can be supported in that environment. And if you go over that, then they run out of resources and then the whole population crashes. Exponential growth, as many of you know from math class, produces a J-shaped curve. So look at the blue line. And logistic growth produces an S-shaped curve. So take a look at the red line. All right, so let's take a look at these models, and my picture is just going to be in the way no matter where I put it today. I could make it go away, but so exponential growth, and again, we're going to model it, but it's not necessarily what most populations experience. The growth of a population continues indefinitely, and it assumes that there are no resource limitations. So I've got an infinitely large beaker with an infinite amount of nutrients, and those bacteria can grow infinitely. So this is how we would describe that growth. It's the change in number of individuals. And let me get my picture out of the way so you can see it. There we go. Change in the number of individuals, and that's represented by dn. And this is a pet peeve of mine. If I understand correctly, maybe I'm misunderstanding something, but I think the reason that we say dn and dt is that it stands for delta. And delta is the triangle. It's the Greek letter delta that means change in. So why they changed it to the letter D instead of the triangle, I have no idea. I'm guessing that maybe it's difficult to make the triangle when you're typing a document, so they just did DN. So whatever, it means delta, and that's change in. So change in number of individuals is delta N, change in the time is delta T, and that's where N represents the population size. R then, if you take a look, you have R max times N. R is the per capita rate of increase, or said more simply, how many offspring per individual. Remember, capita means individual, per capita means per individual. So how many offspring there are per individual in the population. As long as R is a positive value, a population will continue to increase at an exponential rate. Higher R values will lead to faster rates of increase, and you can see that in this diagram. So here's your R value, it's 1, and the steepness of the graph is higher, and here the R value is 0.5. And so we see it's slower, but it's still growing exponentially. If R is 0, the population will not increase or decrease. We'll see a flat line. And then if R is negative, we'll see the population decrease. All right, now more realistically is the logistic growth model. The growth of a population decreases as the population approaches, trying to get my picture out of the way, approaches the carrying capacity of the environment. Okay, so remember that carrying capacity is K. In other words, how fast the population is increasing begins to slow. Let me say that again. I was obsessing with my picture here. The growth of a population decreases. It doesn't mean the population is growing less. Man, I'm awkward this morning. Sorry. It just means that the growth is slowing. So, in other words, how fast the population is increasing begins to slow, and it models resource limitations. The effect of carrying capacity on the rate of growth becomes greater as the population approaches the carrying capacity. So, take a look. We start out in this graph, we start out with exponential growth, but as we start running out of resources, growth begins to slow, and it slows more and more and more the closer we get to K, our carrying capacity. All right, and then this is just another graph showing the same idea with exponential growth on the left. The per capita growth rate doesn't change even if the population gets very large. So we see them increasing at the same rate. Whereas with logistic growth, their growth rate changes depending on how big the population is because it's taking into account limited resources. Okay, so let's talk about real populations. Is it possible to experience exponential growth? Yes. This typically occurs in small populations who are well below their carrying capacity. And in this example here, which was quite some time ago, the elephants were growing exponentially. Their population was growing exponentially in areas where there was plenty of resources for them. Logistic growth, however, is much more common. It's typically populations oscillate around the carrying capacity. So once a population gets fairly large, if they go over the carrying capacity, then individuals start to starve or they start to die. And so you see this, it goes above and then it comes down because the death rate begins to increase. But then once they fall below the carrying capacity, once they fall below K, then there's enough resources so they can start reproducing again. And we see the birth rate start to increase until it goes over K and then it decreases. So we see this oscillation, this going up and down, the overshoot. Look at the Daphnia graph here. They way overshot their carrying capacity and then the population came down. There was a high death rate, a quick death rate. And then we start seeing the population increase again. All right, so then two other things we need to talk about, and then we're done. Density-dependent population regulation. So these are things that will slow the birth rate or increase death rates that have to do with how big the population is. So for example, the most obvious one is competition for resources. If you take a look at the farm field there, those plants are competing for sunlight, they're competing for water, they're competing for nutrients. And so the more and more crowded they get, the less and less of those resources they get. So we see the birth rate decrease. Predation will impact birth rates. So the more predators, the larger the population is getting, the more predators there are because they're feeding on the population. So we see that birth rates start to slow or death rates increase. Disease, we learned this well during the pandemic, and ironically, the picture down below is not from this pandemic, but the more crowded we are, especially in cities, the more likely we are to spread diseases and the more likely we are to slow birth rates or increase death rates. And then territoriality, any organisms that need a specific territory territory, as they become more and more and more crowded, there are fewer and fewer territories that have the resources necessary for them to raise a family, so to speak. And so we see those birth rates slow or death rates increase. And then something called density independent population regulation. This is not about how dense the population is. It's just things like natural disasters. So drought. It doesn't matter how populated or how big the population is. If there's a drought, everybody's affected. Temperature changes, global climate change, for example, and then natural disasters. We saw this very vividly in Australia a couple of years ago. The fires that swept through and the animals that were killed, that didn't have to do anything with how big the population was. All right, ladies and gentlemen, that's it. Now we need to do some problems to try to work through the exponential and logistic growth algorithms. All right, have a great day.